In the year 1887, Hertz observed that electrons are ejected from the surface of metals like sodium, potassium, rubidium when certain radiation is incident on them. The phenomenon of ejection of electron is known as photoelectric effect. He observed that these electrons are ejected as soon as the light falls on the surface of the metal, and he observed no time gap between the incident of radiation as well as the ejection of the electrons. The number of electrons ejected depends on the intensity of the light radiation that is used in the experiment. Intensity means I refer to the brightness, whereas energy or frequency tells the color of the radiation. For example, if I consider violet light, which is capable of ejecting electron from a metal surface. Let me consider dim violet light as well as bright violet light. Both these lights, the dim violet and bright violet, has same frequency, and the dark violet light has higher intensity and dim violet light has lesser intensity. Each metal has a characteristic frequency below which photoelectrons will not be ejected or emitted, and this particular frequency is constant for a metal and we term it as threshold frequency, which is denoted by nu naught. At all the frequencies greater than the threshold frequency, ejected electrons comes out and they gain kinetic energy and they move away from the metal surface. Kinetic energy of the photoelectrons that depends on the frequency of the light radiation that is employed. More is the frequency of the light radiation that is employed, more is the kinetic energy of the photoelectrons emitted. These experimental observations could not be explained by classical theory. It is because according to classical theory, the kinetic energy of the ejected electron, it purely depends on the intensity of the light, whereas the experimental observations showed that kinetic energy of the ejected electron was purely dependent on the frequency. It was independent of the intensity of the light radiation that is used. A clear explanation of photoelectric theory was given in the year 1905 by Albert Einstein. Einstein told that when a photon of sufficient energy strikes an electron present in the atom of a metal, the energy of photon is transferred immediately to the electron and spontaneously the electron is ejected out of the metal surface. So, the phenomenon of photoelectric effect is instantaneous. More is the energy of the photon, more will be the kinetic energy of the ejected electron. In other words, the kinetic energy of photoelectrons was dependent on the frequency of light radiation. There is certain minimum amount of energy that is required for the ejection of electrons from the metal surface. This minimum energy is termed as work function and that is represented by the mathematical expression h nu naught. And the incident photon also has an energy of h nu. The difference between these two energies will be converted as kinetic energy of the ejected electron. And therefore, we can tell that the total energy of the ejected electron is the sum of its work function as well as the kinetic energy. And therefore, the expression h nu is equal to h nu naught plus kinetic energy. As the intensity of the photon increases, the number of electrons which are ejected from the metal surface also increases. Therefore, the number of photoelectrons are directly related to the intensity of the radiation that is used. The phenomenon of photoelectric effect and black body radiation cannot be explained by wave nature of radiation. It can be explained only considering particle nature of radiation. Whereas the phenomenon of interference and diffraction are explained based on the wave nature of radiation. Now, this led to a great confusion whether to consider wave nature of radiation or to consider the particle nature of radiation. Finally, scientists concluded that electromagnetic radiations behaves both as a wave and as a particle. Therefore, electromagnetic radiation has a dual nature. That is, it behaves as a particle as well as a wave. This is also called as wave-particle duality of electromagnetic radiation.